Hello students, welcome to third part of electric charge, Coulomb's force and electric field. In this session, we will learn about electric field. But before explaining this electric field, I will want to tell you one more thing, that is test charge. Because this concept of test charge is used in many places for calculating or obtaining the direction of electric field or force. So what is a test charge? Test charge is a very small positive charge, extremely small positive point charge. It is assumed that it has no electric field around it. Therefore, the test charge exerts no electric force on the charges placed nearby it. Therefore, if there is another charge placed like this is a test charge plus Q0, then there will be force experienced by this test charge due to this charge Q. But this charge plus Q will not experience any force due to charge plus Q0. Now, the test charge is not any real charge. This is imaginary charge for our concept, but even then it is important because it is helpful in obtaining the directions of electric field and force acting on the charges. Now we will come to our next point, electric field. What is electric field? Let us consider a charge plus Q. Then there exists a space around this charge plus Q in which electrical effect of this charge is experienced. How will you experience the electrical effect of charge plus Q inside this space? To experience this effect, we will consider this test charge. We will place a test charge Q0 inside this space. Then, as you know, this charge plus Q will exert a repulsive force on this charge Q0. So, inside this space, this repulsive force will be experienced, and outside this space, if we place this test charge Q0, there is no force experienced by this test charge. So there exists a space around each charge in which the electrical effect of that charge is experienced. This space is known as electric field. Now we want to calculate the intensity of electric field at a particular point from this charge plus Q. Suppose this point is P. So we want to calculate the intensity of electric field at this point P. We will place a positive test charge Q0 at this point, and what will happen? As we know, this charge will exert a force on test charge. Let this force is capital F. Now the electrical intensity at this point P will be the ratio of this force and this test charge Q0. So capital E is equal to F upon Q0. Here this test charge is extremely small. So we will write this expression along with limit as capital E is equal to limit Q0 tending to 0 F upon Q0, because this test charge is extremely small. Now, electric field is a vector quantity. Unit of this electric field is Newton per Coulomb. From here you can see the unit of force is Newton and charge is Coulomb. So unit of electric field will be Newton per Coulomb. In further next chapter we will study another formula for electric field E is equal to V by D. From this relation we can obtain the unit of electric field as volt per meter. Also the dimensions of electric field is MLT minus 3 A minus 1. Now how will you find this direction of electric field? The direction of electric field is always along the direction of force acting on the test charge at that point. So here at point P, the direction of electric field will be along the direction of F, that is force acting on the test charge at that point. Now next is electric lines of force. So to obtain electric lines of force, I will consider a charge plus and we try to obtain the electric lines of force of this charge. So what will we do? We again use this test charge. We will take a test charge and place nearby it, and we will leave it freely to move. This test charge will experience a force of repulsion due to this positive charge and will move along this path. Similarly, if we place the test charge here, it will move along this path. If we place the test charge here, it will move along this path. Similarly, if we place here, it will move along this path. Here it will move along this path, and so on. So we can obtain the electric field of a positive charge by using this test charge. So these lines are known as electrical lines of force. So what are electrical lines of force? An electric line of force is that imaginary smooth curve drawn in an electric field along which a free isolated unit positive charge moves. Here I have shown few electric lines of forces. Here electric lines of forces due to a positive charge. Here electric lines of forces due to a negative charge, because when we place a positive test charge here, it will go along this path, so the direction will be like this, inwards. Similarly, here is a extended surface having positive charge. The electric lines of forces are perpendicular to its surface as shown in this figure. Also, we can draw electric lines of force due to a couple of charges. Here the couple of charges are having opposite charges, and here the couple of charges are having positive charges. So these are the few examples of electrical lines of forces. You can easily understand by using this test charge. Now properties of electrical lines of forces. First thing, if we want to obtain the direction of electric field at any point of the line, then what procedure will we adopt? Suppose that this is an electrical line of force and we want to calculate electric field at point P. So to find out the direction of electric field at this point P, we will draw a tangent along this point, and this tangent will provide the direction of electric field at this point. Now, electric field are open curves. If we consider electric line of force due to a couple of positive and negative charges, then what will happen? Electric line of force will emerge from positive charge and finish at negative charge. it forms a open curve. So electric lines of forces are open curves. But if the electric field is produced by time varying magnetic field due to induction, in that case electric field will be a closed curve, and such fields are non-conservative in nature. Two electric lines of forces never intersect each other. You can see, if there are two electric lines of forces like this, and if they are intersecting at point P, then you can easily notice, you can draw two directions of electric field at point P, which is never possible. At a particular point, two direction of any field is not possible. So two lines of forces never intersect each other. Electrical lines of forces are perpendicular at both the surfaces from where they start and finish. Suppose that electrical lines of force start from here and finish here. Then you can notice that here it is perpendicular, and here also it is perpendicular. So electrical lines of forces are perpendicular at both the surfaces from where they start and where they finish. Electrical field inside a conductor is 0. So no lines of force pass through it. As you can see, in this case also, there are no electrical lines of forces inside the conductor. In the regions where electrical lines are very dense, electric field is strong, and if the lines are rarer, electrical field will be weak. Electrical lines of forces have a tendency to contract in length like a stressed string, and this explains how the opposite charges experience a force of attraction. Similarly, they also have a tendency to move away in the direction perpendicular to its length. Hence, like charges repel each other. There is one more thing to notice here, and that is the lines of force are imaginary, but the electrical field they represent is real. Now we will use the concept of test charge and electric field to calculate the intensity of electric field due to a point charge. So here we will consider a point charge plus Q situated at point O, and we have to calculate the electric field due to this point charge at a distance r at point P. So we will place a test charge at point P plus Q0, and first we will calculate the force on this test charge due to this charge plus Q by Coulomb's law. So the electric force on test charge plus Q0 at point P will be written as F is equal to 1 upon 4 pi epsilon 0 K Q0 upon R square. This test charge is positive and this charge is also positive. So the direction of force will be along the line joining both these charges in direction PA. So the direction of force is along PA. Now we will use the definition of intensity of electric field to find out the electric field intensity at point P. As we know, electric field intensity is equal to F upon Q0, So E is equal to F upon Q0. Here in place of F, we will substitute this value of force, that is 1 upon 4 pi epsilon 0 K Q0 upon R square into 1 upon Q0, this Q0. Now this Q0 and this Q0 will cancel out, so we will obtain the intensity of electric field at point P as 1 upon 4 pi epsilon 0 K Q upon R square, and the direction of this electric field will be along the direction of this force. This force is along PA, therefore this electric field will also be along PA. In place of positive, this charge is negative, then the direction of electric field will be from P to O, and the magnitude of electric field will remain same. There will be no change in the magnitude of electric field, only its direction will be reversed. Now, if there is a system having a number of charges at point O, and we have to obtain the electric field due to this system of charges at point P, in that case we will use the principle of superposition. Suppose consider that there are Q1, Q2, Q3 and Qn charges placed at point O, and we have to obtain the electric field at point P due to this system of charges. Then we will calculate electric field separately due to each charge at point P, and then obtain the vector sum of all the electric fields to obtain the resultant electric field at point P. Now next we come to the electric dipole. Electric dipole is a system of two equal and opposite charges placed at a very small distance apart. Here I have considered two charges, plus Q and minus Q. These charges are same in magnitude and opposite in direction, and I have considered that the distance from the center of each charge is small l. This distance between both these charges is very small, so this will constitute a electric dipole. Now electric dipole moment. If we take the magnitude of one charge and multiply it by the distance between the charges, we will get a quantity which is known as electric dipole moment. Electric dipole moment is a vector quantity, and its direction is from negative charge to positive charge. It is written by small p. Its unit is Coulomb meter. Here you will notice that C is capital and M is small. If you write C small, M small, then it will become centimeter. So you will have to remember, when you write the unit of electric dipole moment, you have to write C capital and M small. Now next is polar and non-polar molecules. Here, as you know, any molecule has two kinds of charges: positive charge and negative charge. If the centers of distribution of both of these charges lie at the same point in the molecule, then it is known as non-polar molecule. And if the centers are a little far apart from each other, then it is known as polar molecule. As here it is shown that the centers due to distribution of positive charge and the center due to distribution of negative charge is a little far apart from each other, and hence the shape of molecule is disturbed a little. This forms a molecule to gain polarity. There are many examples of polar molecules like HCl, H2O, NaCl, AgNO3, etc. Here I have considered a HCl molecule in this figure with H plus and Cl minus having a separation of 10 to the power minus 11 meter. I have told you the unit of electric dipole moment is Coulomb meter. There is another unit of electric dipole moment which is known as dBi. One dBi is 3.3 into 10 to power minus 30 Coulomb meter, and also there is one more unit which is known as electron nanometer. 1 electron nanometer is equal to 1.6 into 10 to the power minus 28 Coulomb meter. I have discussed electric dipole in detail. Now I will determine the intensity of electric field due to an electric dipole. The intensity of electric field due to any dipole is determined in three different positions, and first is at end-on or longitudinal position. What is end-on position? Suppose here is a dipole AB and this is the line joining the charges of this dipole. If point P is situated on this line outside these charges, then point P is known to be in longitudinal position. I have considered this dipole to be placed in a medium of dielectric constant K, and O is the midpoint and L is the distance from the center of both the charges. We have to determine intensity of electric field due to this dipole on longitudinal position at point P. The distance of this point from the center of the dipole is smaller, so distance of this point P from charge plus Q will be R minus L, and the distance of point P from charge minus Q will be R plus L. To determine the electric field at point P, we will evaluate the electric field due to plus charge and then electric field due to minus charge, and then we will find the resultant electric field at point P. First, the electric field at point P due to charge plus Q will be E1 is equal to 1 upon 4 pi epsilon 0 K Q upon R minus L whole square. Since R minus L is the distance of this point from charge plus Q, direction of electric field E1 at point P is along BP from B to P. This direction can be obtained at point P by using a test charge. The force due to this positive charge acting on a test charge placed at this point will be from B to P, and that very will be the direction of electric field E1. Similarly, the electric field due to charge minus Q at point P will be E2, because minus Q will attract the test charge at point P. So the electric field at point P due to charge minus Q will be E2 is equal to 1 upon 4 pi epsilon 0 K Q upon R plus L whole square, and this will be in the direction PA. The direction of this electric field can also be obtained by using a test charge placed at point P. Now we will obtain the magnitude of resultant electric field at point P. To obtain the magnitude of electric field capital E at point P, we will see here separately, because electric field is a vector quantity and we will have to use principle of superposition. Here there are only two electric fields, so we will have the vector sum, and to find the resultant electric field, that is E, this will be under root E1 square plus E2 square plus 2 E1 E2 cos theta. Theta is the angle between E1 and E2. From here it is clear that angle between E1 and E2 is 180 degree. So we will substitute the value of 180 degree to be -1, and we will obtain it to be under root E1 minus E2 whole square. So capital E is equal to E1 minus E2. Now you can say that it can also be written as E2 minus E1. Why it is written E1 minus E2? The answer is very simple. You can see here the positive test charge will experience a greater force of repulsion due to this charge plus Q, because charge plus Q is nearer to P than minus Q, and the attraction force on point P due to this charge minus Q will be less. So electric field E2 is smaller than electric field E1, and hence the magnitude E is equal to E1 minus E2. I have written here in vector form, and this equation is written in magnitude form. Now we will come to this equation and substitute value of E1 and E2 from these two equations, and then we solve them to obtain electric field at point P to be Q upon 4 pi epsilon 0 K into 4 RL upon R square minus L square का whole square. Now we will rearrange this equation. 1 upon 4 pi epsilon 0 K and 4 RL into Q will be written as 2Q into 2L into R. From here, as we know, Q into 2L will become P, so this will become 2PR upon R square minus L square whole square. Now we will see one more thing. If this distance R of point P from the center of the dipole is much greater than small l, in that case square of this distance will be very much greater than this distance. In that case we can neglect this L square in comparison to R square. So here we get R square means R to power 4. 1 R will cancel out, and we will here obtain E is equal to 1 upon 4 pi epsilon 0 K 2P over R cube. If this dipole is situated in vacuum or in air, in that case we know that the value of dielectric constant K is 1. We will substitute K here 1. For that case we may obtain the electric field E is equal to 1 upon 4 pi epsilon 0 2P by R cube. Now the direction of electric field at this point P. The direction of electric field means resultant electric field at point P is along the direction of electric dipole moment